In section 5.5, we're going to look at a very powerful tool when evaluating integrals. It's called the substitution rule. We use this rule so often, a lot of times we'll just call it a U-sub. Now it's a little bit hard to see how the rule works when looking at this property in the theorem. But pretty much what you want to do is you want to take a piece of your integral and let one of that be your u, and then the other piece would be the derivative. You'll end up with an integral that's simpler, that looks like a function of u du. Again, that's very difficult to understand when you just look at the theorem. So let's see in example 1a how we would use this. Notice that in example 1a, if I were to evaluate this integral, I would have to multiply out the x to the fourth minus 3 times, and then multiply that by 2x cubed. That is difficult and tedious. So instead, what I'm going to do is notice that x to the fourth minus 3, if I were to take its derivative of what's inside those parentheses, I would get a 4x to the third, and I don't really care about the constant number part, I just care about the variable. So the x to the fourth derivative would be 4x to the third. So what I'm going to do is, I'm going to let u equal x to the fourth minus 3, what's inside the parentheses. Now if I take the derivative with respect to x, that's going to be 4x to the third. Okay, so my goal is to substitute everything in this integral so it's all in terms of the variable u, which means I need to replace all the x's, including this dx. But notice in the derivative that I just made, I can solve this for dx. And I would get du over 4x to the third is equal to dx. So now let's just do a substitution here. I'm going to have the integral of 2x to the third. The x to the fourth minus 3 is u, so it's going to be times u to the third. And then my dx is du over 4x to the third. I cannot evaluate this integral because I'm supposed to be integrating with respect to u, and I still have x's in here. But notice that the x to the thirds will cancel because of the clever choice of my u. And I can also reduce the 2 over 4, right, to 1/2. So this is what the integral will now look like. It'll be 1/2 u to the third du. And now everything is in terms of u. So with integrals, we can take out a constant. I could take out the 1/2. Not really necessary. I could still evaluate this with the 1/2 in there. And then the u to the third becomes u to the 4 over 4. And we're multiplying here. And then it's going to be a plus c. Okay, so the problem is that I started out with x's. This u substitution is a temporary substitution just so that I can evaluate this integral. So I'm going to have u to the 4 over 8 plus my constant c. However, originally u was x to the 4 minus 3. So this is x to the 4th minus 3, substituting back in for the u, over 8 plus my constant c. And that's the idea behind the u substitution, or the u sub, is you do a temporary substitution, make sure your integral is only in terms of u. Once you've evaluated the integral, then you substitute back in for u. Let's try another example. In part B, now see, that's a quotient, and we don't have the quotient rule for integrals. So what's bothering me here is that square root in the denominator. Now this one's going to be a little bit crazy. I'm going to go ahead and I'm going to let u be x minus 1. So when I take the derivative of u with respect to x, that's just 1. So notice that if I were to solve for the dx so I can replace it in my integral, I have du is equal to dx. Let's look at what that looks like. This integral is going to have an x squared over the square root of u times dx is du. So I have a problem here. The problem is I was not able to get rid of my x squared. It didn't cancel, and I cannot evaluate this integral until everything's in terms of u. However, notice that if u is equal to x minus 1, what that tells me is that x is equal to u plus 1. So x squared is equal to u plus 1 squared, which is equal to u squared plus 2u plus 1. So what I can do inside my integral is I can replace the x squared with u squared plus 2u plus 1. And remember, this is all over the square root of u, which I'm now going to write as u to the 1/2. Everything is now in terms of u. However, it's still a quotient in my integrand. But remember, I can break this all up as u squared over u to the 1/2 plus 2u over u to the 1/2 plus 1 over u to the 1/2. So what this substitution allowed me to do was go from that square root, which kind of made me stuck. I couldn't evaluate my integral because I had this fraction with the square root in the bottom, to just this single term that I can break up and simplify. My integral now will be u to the 3/2 plus 2u to the 1/2 plus u to the negative 1/2 du. Evaluating, I get u to the 5/2 over 5/2 plus 2u to the 3/2 over 3/2 plus u to the 1/2 over 1/2. And then I have my constant c. We'll go ahead and clean this up a little bit and then substitute back in for u. This will be 2u to the 5/2 over 5 plus 4u to the 3/2 over 3 plus 2u to the 1/2 plus c. So now that I've cleaned it up, I'm going to substitute back in the x minus 1 for u. We get 2x minus 1 to the 5/2 over 5 plus 4x minus 1 to the 3/2 over 3 plus 2x minus 1 to the 1/2, again plus that constant c. Again, this substitution is just a temporary substitution, and it just helps me evaluate integrals where I have products, quotient, or chain rule. All right, so let's go ahead and look at another example. We were looking at indefinite integrals, so we didn't have limits of integration. That meant that we had to leave that constant c at the end. But we can also evaluate using substitution with indefinite integrals. And now the problem is that if you're using a substitution to evaluate the definite integral, remember that my limits of integration are in terms of x. So if I'm going to use a substitution, I have to substitute for those limits of integration as well. In this first example, the problem is I have this quotient, and in the denominator it's an x plus 3. Now if it was just x squared, that would be no problem. But in parentheses I have the x plus 3 squared. That's a problem. So what I'm going to do is I'm going to let my u equal the x plus 3. And then that would just mean I have a u squared, which I can deal with. So the derivative, of u with respect to x is equal to 1, or in other words, du is equal to dx. I also have to change my limits of integration. Notice that if x is equal to 3, then my upper limit of integration is going to be u equal to 6. Again, I'm just using the substitution that u is x plus 3. And if x is equal to 0, which is my lower limit of integration, then u is equal to 3. Now our integral is going to be the integral from 3 to 6, because I had to change my limits of integration. This is 1 over u squared. And then my dx is just du. So everything, including my limits of integration, are in terms of u. This is the integral from 3 to 6 of u to the negative 2 du, which is u to the negative 1 over negative 1, evaluated from 3 to 6. I do not have to substitute back in for u because I changed my limits of integration. This is easier to evaluate if you write it as negative 1 over u. So we have negative 1/6 minus a negative 1/3. And then that's just going to end up being a positive 1/6. Typically, I change my limits of integration all the time. However, remember when we looked at our indefinite integrals? We didn't change the limits of integration because there were no limits of integration. And that meant that at the very end, we had to substitute back in for u. So let's look at what happens if you don't change your limits of integration. So if you don't change the limits of integration, but we still let x or u equal x plus 3. So this is where we're at. If I don't change my limits of integration, I leave them off because the limit from 0 to 3 was in terms of x, not u. So you could leave off your limits of integration until you substitute back for the u. I don't usually do this because oftentimes when I'm evaluating my integrals, I'll forget and I'll use the original limits of integration instead of the ones that should have been changed. So again, we had the integral of u to the negative 2 du, which was u to the negative 1 over negative 1. And again, I'm leaving off those limits of integration until I substitute back in for u. This was negative 1 over u, which is now negative 1 over x plus 3. I'm back with my variable x. I can use my original limits of integration. So either change the limits of integration or just leave them off until you substitute back in for u. Because remember, these original limits were in terms of x, not u. Now we have negative 1/6 minus a negative 1/3, and we're exactly where we were before, with the solution as 1/6. So let's do a few more examples. Example B with this definite integral. What I wanted to notice was in one of the parentheses I have x to the third. In the other parenthesis I have an x squared. So when I choose my u, I'm always going to choose the x with the higher exponent, which means I'm going to let u equal x to the third plus 2x. My du dx is going to be 3x squared plus 2. So something I wanted to point out to you is that 3x squared is that second set of parentheses. So what if I just look at this whole piece, the 3x squared plus 2 dx? That's going to be 3x squared plus 2 dx, which means I can substitute this whole piece with du. Now I don't want to forget to change my limits of integration. If x is equal to 1, that means u is equal to 3. If x is equal to 0, then u is equal to 0. My integral is now 0 to 3, u to the 10 du. So much nicer. So this would be u to the 11 over 11 evaluated from 0 to 3. Which is just 3 to the 11 over 11. And I'm going to leave it like that. You could easily just plug this in a calculator and round it off. One more example. Okay, again, I have this product of trig functions. I don't know how to integrate that. What I do notice is the derivative of tangent is secant squared. So I'm going to choose my u to be not tangent squared, just tangent. So the derivative of u with respect to x is going to be secant squared x, or du is equal to secant squared x dx, which is this ending piece. So I can replace secant squared x dx with du, and then my tangent squared is u squared. All I have left is my limits of integration. So if x is equal to pi over 4, that means that u is equal to tangent of pi over 4 is 1. If x is equal to 0, then u is equal to tangent of 0, which is 0. This integral now becomes the integral from 0 to 1. The tangent squared is u squared. Secant squared x dx is du. Huh, that looks familiar. So this is going to be u to the third over 3, evaluated from 0 to 1. Again, if you change your limits of integration, you don't have to substitute back for u. This is simply 1/3. Okay, now we're going to go and do one last example. I wanted to make sure we had a whole bunch of different ones. Okay, cosine squared. I could use a u substitution for this. Maybe. This is the integral from 0 to pi over 2 of cosine of x times cosine of x. And actually, u substitution's not going to help me here. Instead, I'm going to have to go back to replacing this cosine squared with an identity. So remember, cosine squared of x is equal to 1/2 times 1 plus cosine of 2x. So u substitution didn't help. I have to go back to using a trig identity to clean this up. So the integral from 0 to pi over 2 of 1/2 1 plus cosine of 2x dx. And now if I choose, I can pull the 1/2 out. And we can just go ahead and evaluate this, but instead of evaluating it, the 1 plus cosine of 2x. What I'd like to do instead is do a substitution. Now I don't have to. We evaluated this type of integral before without a substitution. But keep in mind that this 1/2 is multiplied by this whole integral. So if I did decide to break this up into two integrals, where I have a 1 dx plus the integral of cosine of 2x dx, then the first integral is just going to be x. However, with this second integral, instead of using that property we had before that said this would be 1/2 sine of 2x, I'm actually going to derive that property. So the issue here is that it's not a cosine of x, it's a cosine of 2x. So I'm going to change it by letting u equal 2x. So my du over dx is 2. I'm going to isolate the dx and write du over 2 is equal to dx. If x is equal to pi over 2, then my u, which is just 2x, is going to be equal to pi. If x is equal to 0, then u is equal to 0. So this first piece, the integral of 1, that's just going to be x evaluated from 0 to pi over 2. This second piece, I've done a u substitution with that. Now I still have the 1/2 that I need to distribute. But now this becomes the integral. 0, pi is the upper limit. The dx is du over 2. The cosine of 2x now becomes cosine of u, and this is times du over 2. Okay, so this first piece is going to be 1/2 times 1/2 minus 0 is pi over 2, minus 0 is just pi over 2, so it becomes pi over 4. This second piece is all in terms of u. That would be 1/2 times the integral of cosine is sine of u. And then we have this du over 2, which is a 1/2. So what I'm going to do now is I'm going to pull that 1/2 out, and this 1/2 in the front becomes 1/4. So that's just sine of u evaluated from 0 to pi. First piece becomes pi over 4. This second piece here, sine of pi is 0 minus sine of 0 is 0. So this just becomes 0. And the answer would just be pi over 4. So you may be asking, why go through all that trouble when we had this property in the very beginning of how we can integrate cosine of 2x? Well, now you don't have to memorize that property. If the argument is not just x, if it's like a 2x or an x over 4, you can just do a u sub on the argument of these trig functions, and you don't have to remember those properties. So this is it for this section.